The next question of CODECHEF starters 118 is Xorry2. So basically in this question, we are given an integer x and we need to find out number of pairs a comma b which satisfies the following three conditions. That is a or b should be equal to x and 0 is less than or equal to a is less than or equal to b is less than or equal to x. And the next condition is, this is the first condition, second, and the third condition is difference between b minus a should be as small as possible. This is the third condition. So we need to find out number of pairs a comma b which satisfies all these three conditions. So if we look at the constraints of this problem, constraints are there can be 1 to 10 power 5. Test cases can be in the range 1 to 10 power 5 and x will be in the range 1 to 10 power 9. Let's see how we can solve this problem. So here we can observe firstly x can be in the range 1 to 10 power 9. So that means there can be at max 30 bits, right, in the binary representation of any number. Any number in the range 1 to 10 power 9 can be represented with 30 bits in its binary representation. So now let us consider x with some binary representation 0, 0, 1, 0. So let's say this is the binary representation of x. So this is 0th bit, first, second, third bit, fourth bit, fifth, sixth, 8, 9, 10, 11, 12, and 13th bit. So there are 13 bits in it. Now, firstly, let us observe one thing. So now our aim is to firstly make the three conditions satisfy. Find out a comma b such that the three conditions satisfy. That is a or b is equal to x. 0 is less than or equal to b less than or equal to x. And third is b minus a is as small as possible. And the way we make these three conditions satisfies, if there is some bit which is not set in x, let us not set that bit in both a and b. Right? Considering that, so if a bit is not set in x, don't set it in a and b both. So this way, let's find out a possible a and b. So a, b. Now, one small observation is for any bit 2 power I, let's say ith bit, 2 power I is greater than 2 power I minus 1 plus 2 power I minus 2, so on plus 2 power z. So this means 2 power ith bit, let's say ith bit, uh, like ith bit's value is 2 power I. So now though we set all bits lesser than ith bit, still the summation of all the bits lesser than ith bits value is not equal to ith bit, right? It's less than ith bits. So now if you apply GP on this, So we are assuming that the worst scenario can be setting all bits lesser than ith bit. So in that case, we can get this as the value. So if we apply GP, we can observe this is 2 power I minus 1. So 2 power I minus 1 is still lesser than 2 power I. So from this, we could observe that setting 2 power I is will contribute a more value than setting all the bits lesser than 2 power I. Right? So from this, uh, for the first condition to satisfy, that is A or B should be equal to X. Wherever we have a set bit in X, that should be set in either A or B, but it shouldn't be set in both. Right? So from the below observation, it is always optimal for us to set the most significant bit, which has the highest value in B, and all other set bits which are present after it in A. Right? And as we discussed, wherever there is a 0 in X, we won't set it in any of them. If some bit is unset, we'll keep it unset only. Okay? So all these bits are unset, so we put all these bits as 0 in A and as 0 in B. So these all are unset bits in X, so we kept it as 0 only. Now, the set bits, if we observe MSB, we kept it in B, so we shouldn't put it in A. And seventh bit, we kept it in A, so we shouldn't put it in B. Similarly, fourth and third, we kept it in A, so we shouldn't put it in B. And first bit, we kept it in A, so we shouldn't put it in B. Now we can observe that if we XOR A and B, the result will be X, right? And we can even prove that for this kind of arrangement, B minus A will be as small as possible. That is because from the below observation, we just saw that 2 power I is greater than uh, 2 power I minus 1 plus 2 power I minus 2 and so on, right? So it is greater than the contribution of sum of all the bits lesser than the current bit, lesser than the ith bit. So from this, we can observe that if we are putting MSB in B, then basically we are putting 2 power 11 over here. Now, though we add 2 power 10, 2 power 9, so on till 2 power 0, still the value won't reach 2 power 11. Right? Now, among these values, we don't have few values. That is, we only have 2 power 7 plus 2 power 4 plus 2 power 3 plus 2 power 1. Right? This is the values that we have, which are set and less than 11th bit. So if we put any of this value in B, that will just increase B, right? So increasing B is useless, but instead making B constant and then increasing A and bringing A closer to B will benefit us, because that will ensure B minus A value will be as small as possible, right? So that is why though we add all the bits from 2 power 10 to 2 power 0, it couldn't reach 2 power 11. Then for sure, a subset of all bits from 10 to 0 will also not reach 2 power 11. But by putting all such bits lesser than 11, which are set in X in A, can push A's value closer to B, which will ensure B minus A is as small as possible. So that is why we arranged all the other bits in A apart from the MSB, and this is how we proved B minus A is as small as possible with this arrangement. Right? So we know that this is one arrangement. Right? So we know that this is one arrangement which will satisfy all the three conditions. Now we know this is one arrangement. So now In this arrangement, wherever we have a unset bit in X, we kept it unset only in A and B, right? But there can be few cases where we can set those bits. Like this is one possible A comma B pair, but if we observe, though I set this bit here, still it will satisfy all the three conditions, because when we XOR, these two values will become zero, right? Because it's set in both. Now we need to find out how many positions are there, how many positions in X are there which are zeros, and which can be kept as one in A and B both. So if we know that, then it's just we'll have two choices for every such position. So let's say number of such positions, number of unset bits in X which can be made as one in both A and B are C. Then number of different AB pairs that we can form are 2 power C, right? Because for each such position, we'll have two choices. Either put 0, 0 in A and B both, or put 1, 1 in A and B both. And if there is a set bit, then we only have one choice. We should set that bit in one of the number and unset it in other number. And we know always this configuration is better for a set bit. Putting the MSB in B and restoring A. Now, the claim is, how do we count this C? So when we are counting the C, like when we make two bits, when we make a bit which is unset in A and a bit which is unset in B as set, then these two conditions won't violate, but this condition might violate, right? The second condition. So we should ensure that second condition won't violate. That is because we are adding a bit, we are making a unset bit set. So what can happen is the value of B can go more than X. So we shouldn't allow that to happen. So now let's see how many bits we can set them to 1 in both A and B such that the second condition won't violate. Now if we observe, if B won't violate the condition, then for sure A also won't violate, right? Why? Because B is greater than A. So if larger number itself is smaller than X, then smaller number will for sure be less than X, as we are setting the bit in both A and B. So now if we observe, uh, here we can't set a bit, right? Here we can't set a bit, as if we set a bit that will make B value greater than X. So firstly we observe that any unset bit any unset bit after MSB of X can't be turned to 1 in both A and B, right? So here we have only one choice. Here also we have only one choice after MSB. Now let's see. Okay, if we look from right to left, then it's before MSB. So all the bits before MSB can't be set to 1, as that will increase the value of B more than X. Now, at the position of MSB, because it's a set bit, we don't have any choice to make decision, as we should forcefully put it as per how we kept it in A and B. That is MSB in A, MSB in B, and all other bits in A. Now, if we look over the bit, look over the next unset bit after MSB, that is this. Even this bit we can't make it a 1, right? Because that will make B greater than X. Similarly, this bit also can't be made as 1. This bit also can't be made as 1. And this bit also can't be made as 1. Why? Because this is a set bit of X. So let's ignore all set bits for now. So these three unset bits can't be made as 1. Now if we observe, from this unset bit onwards, we can make it as a 1. We can make it as a 1. And here we can make it as a 1. And here we can make it as a 1. Right? That is because here if we observe, though I make this and this as a 1, still my B value will be less than X. Why? Because the first MSB is present in B and the next MSB is present in A, right? So the first most significant bit is present in B, the next most significant bit is present in A. Now, the next, as the second most significant bit is not present in B, now though I make all bits set which are smaller than the second most significant bit, still B value won't exceed X, right? It will still be less than X. So that is the reason why we can make all the zeros after the second MSB in X to ones in both A and B. So now if we observe, now we could just now we could prove that after the second MSB, all the unset bits could have two choices. That is, we can either leave it 0 0 or make it 1 1. So there are two choices for this, two choices for this, two choices for this, and two choices for this unset bit. So according to this, there are 2 power 4 choices. That is, here C is 4, and we have 2 power 4 choices according to this example. So this way, we can calculate the number of pairs A comma B that are possible. So number of pairs which are possible are just all the count all the unset bits. Like if we conclude it, if we conclude all the proofs and observations that we made, then to calculate number of pairs of A comma B, we can just find out how many unset bits are there from the second most significant bit of X. That is here, this is the first most significant bit and this is the second most significant bit. So after the second most significant bit, count how many unset bits are there in X. So here we have 4. Let C be the number of unset bits after the second most significant bit. Then the number of pairs A comma B that we can form are 2 power 4, because for all the bits which are unset after the second most significant bit have two choices. Right? So in total, for 4 such bits, we have 2 into 2 into 2 into 2, which is 2 power 4 choices. So this way we can solve the problem. So to implement this, just iterate a loop from I in reverse order, 0 to 30 to 0, and then put track of the number of most significant bit. So once you encounter the second most significant bit, from then start counting all the unset bits in X. Then it is just 2 power C. So let C be the number of unset bits and it's 2 power C. So for each bit, just iterate and find this out. So as we only use a single loop of size 30, as 30 can be the maximum number of set bits till 10 power 9, or to run a perfect loop, we can iterate from ceil of log base 2 of X. So we can say the time complexity is big of log base 2 of X. And or this can be 30 also if we fix 30 as our limit. And space complexity will be big of 1. All these are per test case. So this way we can solve the problem.